Show beginning. Hello, everybody. So let's get started. This is our fourth talk and the last talk of the morning session. Yeah. So it's my pleasure to be the fourth speaker, the last speaker of the morning session. Biswadip Dey from Siemens Corporation, Siemens Corporate Research, my former employer at Princeton, New Jersey, who's going to talk about physics-informed
machine learning.
That is not. We need to move everything down.
Oh, sorry.
Machine learning for inverse problems. Okay.
Good morning, everyone, and thanks for coming to the talk. So my name is Biswadip Dey. So today I'm going to talk about physics-informed machine learning and how it can be used for certain types of inverse problem. So as engineers, we often find ourselves at the intersection of the real and the digital domain. So on one hand, we have robotic manipulators operating on a factory floor, or we have the melting and solidification process happening during additive manufacturing, or we have power flow through a large complex power grid networks. On the other hand, we can get data from these physical systems, and then we can operate on those data to optimize the design, to find out what is a better process to control the robotic manipulators, or what is the better process for building something through additive manufacturing. Or we can also find out if something is wrong in the system, if there is any anomalous behavior, or if something is wrong, what is causing those behaviors through predictive analytics. And in that context, in many problems, like there is like immense need to learn functions from data, and that's why machine learning provides a very good tool for these type of problems. Now, when we think about machine learning, the typical examples that come to our mind are related to computer vision or natural language processing, where you can relatively easily get huge amount of data or a huge amount of good annotated data. However, for this type of industrial problems, we often lack good quality of data. For example, if we are interested in studying material behavior, then we cannot ask someone on Amazon Mechanical Turk to characterize those behaviors and generate a data set of 1,000 images. But on these type of problems, we often have just give me one moment. We often have lots of domain knowledge, or we know a lot about the physics of this problem. So how we can use that structure? Now, if we think about the problem, it's not a forward problem where we are interested in getting data or running experiments to generate data through the systems, or running the model, simulating the models, but we are thinking about inverse problem. And as we all know, these type of inverse problems are ill-posed. They lack unique solution. For example, if we have a point cloud and we want to fit some curve or surface, then we can have multiple such solutions which will have the same type of test error. So we need to incorporate certain type of structure into the class of solutions that we are will look our answer in. So in terms of RKHs, we need to find out the right type of hypothesis space in the problem. So in that context, we all know about introducing regularization in this type of inverse problem. And now, if we think about regularization, then there are standard approaches like Tikhonov-Ridge regression, or lasso, or spline, or truncated SVD. But in today's talk, we'll focus on a specific type of regularized approaches where the inductive bias would come from a dynamical system. So in this case, we are assuming that the data is coming from a physical system whose dynamics is governed by a set of differential equation. So you can think of Z as the state vector of a system, or in the machine learning language, the latent space of a system, and X is input to the system and Y is the output. So if we have this type of underlying dynamics governing the generation of data, how we can incorporate those type of like appropriate structure in the inductive bias. Now, traditional techniques like RMAX or filtering follows along this line of thought, and more recent techniques like control theoretic splines or sparse identification of nonlinear dynamics or SIMD also work on this type of problem. Now, in the next question is, now neural networks provide a very good approach to learn functional solutions to approximate function. Now, can we incorporate this type of dynamic systems based inductive bias on those neural network based methods? So the goal is how we can incorporate some kind of symmetries or conservation laws into a data-driven approach of learning dynamics from observed data, where the dynamics is governed by some system of ODEs in this specific context. And what we aim for here, so we want to have improved performance on the test set, namely the better generalization performance. We also want to ensure that we can learn more from less data. And as neural networks are often inherently black box, so we want to improve the transparency of those models by incorporating certain structures. So in our approach, we specifically focus on Hamiltonian formalism. So we will see how we can incorporate Hamiltonian dynamics into a neural network structure. So just as a brief introduction to Hamiltonian dynamics in like classical mechanics approach, where we describe the behavior of a system in terms of coordinate or position and momentum variable, and it describes the behavior in such a way that the system evolves always conserves certain quantity, namely the Hamiltonian. And for physical systems, it usually represents the total energy. And the overall dynamics can be governed by this set of differential equation. And in this case, we can see that the dynamics of Q and P always conserves the total energy or the Hamiltonian. So this formulates the symplectic gradient, and that's why we call our approach symplectic ODE-net. Now, for physical systems, we have some more structure. Like for separable systems, we can further split the Hamiltonian into a sum of kinetic and potential energy. And we will see how we can incorporate all these structures into neural network-based methods. Now, as we know, there is a dual formalism through the Legendre transformation described by Lagrangian dynamics. This whole formulation can also be translated to Lagrangian-based methods. But now, if we think about the Hamiltonian formalism, it talks about isolated system where there is no exchange of energy with the surroundings. But we often deal with systems in the physical world which exchange energy. So there is an extension of Hamiltonian dynamics to basically you can introduce additional control term to describe forcing function or external torque into the system. And then this formalism can be used to describe like any system. For example, the canonical control systems like an acrobat or a pendulum on a card problem. Now, if we take it to the next step and ask the question like, but in real system, we don't have energy conservation all the time. Energy is lost due to friction or resistive losses. So this formalism can also be extended to incorporate energy dissipation by introducing this positive semi-definite matrix T and with the additional control term. And now on top of this, if we introduce additional output variable in this specific way, then one can ensure that the rate of change of energy will always be upper bounded by this duality product, and the physical interpretation is your rate of change of energy is upper bounded by the power flow rate. And this provides a very natural formalism to describe a large class of interconnected complex systems where the physics of different subcomponents can be of different nature because everyone is interacting through exchange of energy. So this port Hamiltonian formulation has been used for modeling power grid networks, robotic systems, and even other type of systems. So from that perspective, we are not restricting much by adopting this Hamiltonian formalism. So now The next question is how we can incorporate this type of structure into a neural network-based framework. So in this case, we assume that we have access to the input data and the position and momenta, but not their derivative. So one can use NeuralODE, which is like differentiable ODE solver. It can take any black box ODE solver, and through adjoint analysis, it can give us sensitivity with respect to different parameters, which we'll see how it works. So in this case, we can use a neural network to parameterize the integrand of a differential equation. And then we can use a NeuralODE solver to integrate this equation and obtain the trajectories data. And in this case, as we are solving an ODE, the data that we are going to predict need not be coming from uniform sampling. So they can be irregularly sampled because we are integrating a continuous dynamics. And then we can compare that with the ground truth data that we are observing from the system to define some appropriate loss function and then minimize it to learn the dynamics. And in our proposed symplectic ODE approach, instead of using what we did was that instead of using a single neural network to parameterize the dynamics, we used multiple different subnetworks to parameterize different aspects of the dynamics, namely the inertia matrix or the potential energy or the input coefficients. And we had to do some reparametrization trick to enforce positive definiteness, and so that because neural network without like any additional constraint, we do not have any direct control over the positive definiteness of the matrix. So we use Cholesky factorization for that. And then we can use mean square error to compute the difference between the ground truth and predicted trajectory and try to learn the dynamics. So see how that works. So when we used this approach on data for simple pendulum, we saw that if we just use a simple like black box neural network, the learned model cannot uncover the energy conservation. We can see that in this case, what we are seeing is the ground truth data of position and momentum, and the light green line shows the predicted evolution of position and moment, and we can see that they are always spiraling in. On the other hand, when we enforce all the structure, the predicted trajectories matches fairly well in the ground truth trajectory. And we also considered another like intermediate model where we are using Hamiltonian formalism, but we are not enforcing the constraint that the Hamiltonian is separable. And in that case, also you can see that it matches fairly well with the ground truth, but not quite accurately. So things look good here. But if we look into the learned functions by the symplectic ODE network, we can see that the input matrix or inertia or the potential energy, they match relatively well with the ground truth data. And please ignore the gap in the potential energy prediction because it doesn't matter. So, but we see that there is quite a bit of mismatch around this point. Like when the position is around like minus pi, things are off. But that shouldn't happen because the behavior is pretty good around pi. So what is going on here? The thing is, we are looking into a pendulum where minus pi and pi refers to the same point, but the neural network doesn't know it. So that leads to the next question on how we can enforce this type of angle-aware design, like how we can enforce some constraint that will allow us to deal with angles. So from the theoretical perspective, we typically use the independent generalized coordinate. But however, from a data-driven perspective, it is sometimes easier to deal with some embedded variables where you can enforce this type of ambiguities. So now we are interested in how we can bridge this gap. And also from practical perspective, some of the simulator models that are used in learning community like OpenAI Gym, they generate data in the form of cosine sine embedding. So, and also typically momentum data is not readily available, but the velocity data is more readily available. So how we can enforce this type of Hamiltonian formalism when we do not have direct access to the position or the momenta variable. So in the next few slides, we'll see how we can bridge this gap. And as you can guess, in this case, again, we leverage chain rule, and we first introduce this set of variables, sine, cosine, and q dot, and we assume those to be the state variable. And then we can describe their dynamics in terms of the other variables, and from there we can apply again chain rule and autodiff to find out the gradient of these different variables, and we can plug that into our network, and then we can see when we look at the function learned by this new design, they matches pretty accurately with the position, with the ground truth data. Now, if we take a bit closer look at some other results, for example, how they generalize across multiple tasks. So in this case, we have looked into the pendulum data, but in this plot, I'm showing the mean square error in prediction and how it evolves over a long horizon prediction. So we can see the proposed model shown in blue conserves has the minimum mean square error, and it also conserves the energy fairly well compared to the other methods. And we also ask the question, how does this method perform when we have more data or less data? So when we looked into the effect of the number of data points in the training data set, we can see that when we have very few data, in that case, the proposed model perform fairly well. Now, in this case, we are looking some a bit different for the cart pole system, because we have both the real variable and the angle variable. But in general, we can see the prediction error and the training error, they are quite the minimum for the proposed method. So the main takeaway points from here is that this type of network can achieve better generalization, with fewer training samples, and this angle error design that we introduced in the last few slides can further narrow the gap between model-based and data-driven methods. Now, another degree of freedom that we have over the algorithm is the integration time horizon. Like when we are integrating the dynamics, we can show that we can improve the performance by increasing the integration time horizon, but it comes at the cost of additional function evaluation or compute cost. And finally, this type of framework can also be extended to incorporate energy dissipation into the framework. Now, that angle error design gives motivation to another line of thought. So for this double pendulum, we know that we can describe the dynamics using this independent angle coordinate, but alternatively, one can also express the dynamics in the XY coordinates of the effector endpoint locations. But in that case, they will be constrained. So the system variables will not be independent, rather they will have a holonomic constraint. So can we enforce Hamiltonian formalism when the system dynamics of the configuration space is not unconstrained, but it has some integrable or holonomic constraint? And one can show that in this case, if we assume that the system configuration space dimension is T, and it has the actual number of degrees of freedom is M, then the system has a D minus M number of constraints, and those constraints can be given by this vector valued function phi. Then we can show that the constraint Hamiltonian dynamics can be expressed in terms of the original term plus some additional term, which depends on the Jacobian of this vector valued function phi. And then if we know this constraint function, we can also encode them in the neural network framework. And then we can try to learn dynamics by using those constraint high dimensional data. And when we do that, we notice that so here we are showing the performance of this approach across multiple tasks. One pendulum, two pendulum. So basically it means how many links are there in the pendulum. And we can, in this case, the first bar shows the relative error from the new modified approach, and the other was shows the performance from the different variants of the approach, where one was using the Hamiltonian dynamics based on position or momentum variable. So in this case, we can see that the gap between the performance of the proposed approach compared to the others, they are more prominent when we have more and more complex systems, especially for a three-dimensional system like gyroscope. We get several orders of magnitude benefit in terms of the trajectory relative error. And that makes sense, because when we have more complex systems, then the inertia matrix or the potential energy takes much more complicated form in this generalized coordinate. And when we also looked into the effect of the number of training points of the data set size, we can see that the proposed method, which is shown by this black line, is relatively significantly more performant when we have less data. So this can learn better in the low data regime. And to conclude, we can say that these models that enforce this type of explicit constraints are significantly better than the other ones where we have constraints implicitly, but they are more difficult to build because the computation graph is more complicated. You have to compute the additional Jacobian term. Now, before we conclude the talk, I wanted to give a brief glimpse of the next extension, because not everything is continuous, right? Or everything is rigid. For example, when I'm bouncing a ball, dynamics can be governed by Hamiltonian dynamics, except at the point of contact. Or if we think about a soft body or a rope, it can be approximated by an n-link pendulum with some additional constraints on how much it can bend or how much it can stretch. So can we incorporate these models to accommodate this type of contact, collisions, or constraints? So we have been exploring these questions recently, and in that context, to model the contacts or collision, we can use the maximum dissipation principle and split the contact phenomena into two phases, a compression and restitution phase. And then one can show that we can resolve the contact velocity, or namely the velocity correction that we need to capture the contact phenomena through a convex optimization problem. And that can be done using the differentiable convex optimization. So Dr. Coulter is here. So we are following his work on CVX by layer, where we can parameterize the input to the convex optimization problem through neural network or through other learnable parameters, and extract those parameters of friction coefficient or coefficient of restitution. And then we can see that we can simulate the whole dynamics through by interviewing this type of ODE integration and contact model solution. And then once we have this framework, and if we compare that with the ground truth data, we can construct some appropriate loss function. And as each of these models are differentiable, we can pass the sensitivity through each of them and find out the basically different parameters associated with the system dynamics or contact properties. Now, there is another aspect to it. In this case, we are trying to learn the dynamics or the different parameters associated with them. And on the other hand, if we know this dynamics, we can use the same framework to backpropagate it through this whole process and find out what should be an optimal initial position or velocity, so that some cost metric on the trajectory points can be minimized. So we can also use the same framework for planning or control purposes. And finally, I'll show you some videos. Here, we are showing 3 different tasks on predicting the movement of disk, like moving and rotating on a floor, a chained pendulum, and a gyroscope, which can also hit the wall. And the left panel shows the ground truth behavior, and the right panel shows the predicted behavior, where we have learned the dynamics from past observations, and we are using it to predict the behavior. And we can see that the predicted behavior matches the ground truth fairly well. And we can also look at the learned parameter values. They also match fairly well with the ground truth values. And the performance on the planning task, also in this case, we are trying to find out the optimal initial velocity of the ball so that it hits the target after the first bounce. And we can see that when we are learning the dynamics and then using this framework that I described on the previous slide to find out the initial condition, they match fairly well with the behavior that that would have been obtained if we were using the true values. And the same thing, we are doing another experiment where we want to find out the optimal like initial position and velocity of the white ball, so that once it hits the delayed balls, the blue ball goes to the target at certain time step. So that was all that I wanted to talk today. So the main key takeaway is that by incorporating this physics-based structure, we can improve the performance of the neural network. Namely, we can improve the generalization behavior, or we can learn more from less data. And this work wouldn't have been made possible without my amazing collaborators, Amit and Desmond. And if you have more questions, please feel free to reach out to me. Thank you.
Yep, time for questions.
So, my impression with all these eclectic techniques, the reason they do so well is that they're basically under the hood satisfying Louisville theorem. Is that what's going on here?
Yeah, and we are enforcing the same structure here. Yeah.
And does that still work when I have a non-separable Hamiltonian, or I'm adding energy to the system?
Yeah. So if we go back, so one of the model variants that I was showing, which was not performing well in this case because we had a separable Hamiltonian, but in those cases, those models would be better performant because we are using a neural network to learn the Hamiltonian without any additional structure. And like injecting additional energy, so we have seen through this additional term, right? So in these systems, for example, when we are hitting the ball in the like decision in the planning task, the energy is not conserved. And also when we are thinking about this frictional coefficient, the energy is not going to be conserved. So those cases there.
And that, the rolling ball, that's non-holonomic as well.
No, in this case, you mean the nose, this one, right? So yeah, yeah.
Does this work at all for non-holonomic?
So we haven't incorporated that non-holonomic constraint. Yeah, because that's another extension that
Can you say a little bit more about the changing dynamics of perspective? Do you get sort of like what is, how easy is it to find like that makes the difference?
You mean in terms of the optimization algorithm that we used? Through like so I cannot say anything from theoretical perspective. We don't have any guarantee, but through empirical validation, we haven't encountered the problem of local minima in our approach, and we are using off-the-shelf Adam algorithms. So.
Some other non-linear function in the approximation to get the Lagrangian metrics,
in this case, we assume that we know the constraints and then compute the Jacobian analytically and incorporate that. But that's that's another direction that can be taken. Like, can we learn the dynamics and the holonomic constraints together? So.
More questions? Yes.
You mean, I'm not very familiar, but I have seen some work on connecting the Navier-Stokes with Hamiltonian dynamics on the space of diffeomorphism. Are you thinking along that? So could be, but that would be some additional requirement because this is for finite dimensional system, right? But in that case, I think the Hamiltonian flow is on the space of diffeomorphism. So, right. So yeah, we can talk offline about that.
No more questions. Let's send the speaker again. And to complete the morning session, we have an hour and a half break for lunch. And we'll reconvene here at 1:45.
Quick announcement.
Yes.
So first of all, we have a screen here, a table, and they control